What is electroplating? Well, basically, it is the process of coating a layer of metal on another metal. We will be explaining the details of this process later on in this documentary.
Modern electrochemistry was invented by Italian chemist Luigi V. Brugnatelli in 1805. Utilizing the voltaic pile discovered by his colleague Alessandro Volta in 1800, he performed the electrodeposition of gold.
Electroplating is usually applied to practical science and engineering. Common applications include tin-plated steel cans to ensure food safety and hygiene during mass productions, and gold or silver plating of jewelry to enhance appearance. It is also used in the automobile industry to enhance corrosion and rusting resistance, forming a protective layer against oxidation. The products of electroplating can vary from many metal-plated objects, such as silver-plated mouthpieces for brass instruments, to metal machine parts used in industrial processes.
Electroplating is important to society since it aids us to manipulate resources around us in order to suit them to our needs, essentially making life easier. Other applications of electroplating are to make an object shiny and create a mirror-like image finish for objects. It also increases an object's durability and provides insulation. Electroplating can also change some of the chemical properties, like conductivity, solderability, and paint adhesion.
Our experiment was set up with copper sulfate and silver nitrate. Each substance was conducted through the electroplating process 5 times, each time with a different amperage. This way, we can determine the relativity between amperes and mass gain for each object.
The object of choice was a $1 coin. A Hong Kong $1 coin is made from steel, which is 99.8% iron and 0.2% carbon. Its outermost layer is nickel.
The other materials used were a power source, wires with alligator clips, ammeters, variable resistors, copper sulfate solution, silver nitrate solution, a graphite electrode, vinegar, and glass rods.
The coins were lightly sanded to get rid of the rust, and then washed with vinegar to ensure that the surface of the coins were not contaminated by other impurities. The objects were then weighed and clearly labeled and placed on a piece of tissue paper.
This is what our setup looks like. The cathode end of the power source is linked to an ammeter, which shows the current moving through the wire, and then to a variable resistor, which allows us to control the flow of ampere along the wire. Lastly, the wire is linked to the coin and then into the solution.
The power source provides a supply of flowing electrons. The positively charged electrode is a stick of graphite. We chose graphite instead of copper because graphite has a special property of electric conductivity, despite the fact that it is not a metal. Also, the graphite ions are non-reactive, therefore it would not affect the accuracy of the results.
We first tested a coin with copper sulfate to make sure the electrical components were working. However, there was no reaction because of a mix-up of positive and negative charges, and there were some minor issues with the power unit and ammeter. Eventually, all the problems were diagnosed, and the experiment began.
3 systems were run simultaneously. Each experiment lasted 10 minutes. When the stopwatch started, the power unit was switched on, and the amperage for each experiment was tuned, according to the variable resistors.
The first coin was plated with copper sulfate through a current of 100 milliamps. The original features on the coin were still quite obvious, with a thin layer of pink coated on top.
Likewise, the second plating was conducted with a current of 200 milliamps. There was an increase in the thickness of copper coating plated on the coin, but we could still make out the coin's external features.
The third coin was plated with a 300 milliamp current. The copper plating on the coin was much darker compared to the other coins, and its features were barely visible.
A current of 400 milliamps was used to plate the fourth coin. This process created a more consistent shade of dark brown copper on the coin, and there were no pink spots left.
The last coin plated with copper was conducted using a 500 milliamp current. The color of the copper plating on the coin was a very dark shade of brown, and the coin's external features were not visible due to the thick layer of copper coated on it.
After conducting 5 trials for copper, our group wanted to see the differences in mass gain between the 2 metals. We chose to use silver nitrate because silver is often used to plate electronic circuit boards and USB cables to prevent rust and enhance corrosion resistance.
We plated the first coin with a current of 100 milliamps. The silver plating on the coin was not too evident because of their similar colors. we realized that the silver was more powdery than copper. The plating of silver was sparser and more irregular than the copper plating.
The second coin was plated with a current of 200 milliamps. Even at that stage, the layer of silver was quite thick and the coin was not recognizable. The silver on the coin was very brittle at the time. Grains of silver would stick on the tissue paper where the coin was placed.
However, the third coin that was plated with 300 milliamps closely resembled the second coin. The thickness of the silver coating over the coin was quite similar to that of the second coin.
The fourth coin was plated with a current of 400 milliamps, and this time there was a noticeable difference in the thickness of the layer of silver. The grains of silver were packed more than before, and there was more silver plated on it.
500 milliamps was used to plate the fifth coin. Due to the problems regarding the ammeter, we had to plate it twice. During our first attempt, the silver plating on the coin was increasing too quickly and it came into contact with our anode, the graphite stick, and the circuit short-circuited. For our second attempt, the ammeter wasn't functioning properly, and as a result, the plating on the coin was very minimal. It resembled the first silver plating in our experiment. This is a graph showing the mass of silver and copper metal gained on each coin in relation to the amount of energy used.
Electroplating reactions can be quite hazardous to the environment. The products of electroplating reactions do not actually decompose because they are usually heavy metals such as cadmium and chromium. Heavy metals can lay dormant in the soil and mud, polluting the environment as they cannot decay.
There have been some efforts attempting to reduce heavy metals by planting plants or using microorganisms. Out of the total amount of metals used, 4% goes to waste. This 4% would have to be expensively treated in order for it to be reused. That is why most industries just throw it out.
If these heavy metals, such as chromium or nickel, get into water sources, the water source will then be contaminated to an extent where it can no longer support aqueous life forms. Waste can also contaminate soil and air. If these ions are not treated properly, it could be released into the atmosphere, resulting in acid rain and contamination of soil for agriculture.
Recently, in the town of Liguozhang, China, there has been problems with nearby electroplating industries. The villagers are unable to drink water from their taps due to the water pollution released from the factories. These electroplating industries manufacture craft goods and jewelry using harmful metals such as cyanide, nickel, and chromium. The water was polluted after these pollutants seeped into the soil and into underground water and the rivers.
Overall, our experiment was a success. Other than one unsuccessful trial with the silver plating of a coin, we were able to gather accurate data for all of the other trials with copper and silver plating.
As we analyzed our labs, we discussed thoroughly about the use of energy through these electroplating processes. The area of the coin submerged in the solution during the reaction was 20 mm by 25 mm, and the average voltage used was 10.3 volts. The amount of copper and silver coated onto the coins were disproportionately low compared to the amount of energy used in the reaction.
This shows that electroplating requires a great source of energy, and since this reaction is constantly used in mass proportions in many different fields of production, the energy is also very high. In our experiment, we discovered that even though coins charged with greater amperage may gain a thicker layer of metal coating, it was very brittle and detaches from the coin very easily. On the other hand, the ones with the lower amperage have more ideal result.
However, the lower amperage requires a longer time for the object to be entirely covered with a layer of metal. So, if a certain factory were to use electroplating processes during their production phase, a lower input of energy would be more ideal if they wished for their products to resemble the original shape more. To compromise with this lower amperage, however, a longer time would be required.
Using a lower input of energy also has its benefits. Not only would the company have more ideal results from the manufacturing procedures, they would also conserve more energy, preventing the exploitation of fossil fuels and other types of harmful sources of energy. Using a proper method of waste disposal and eliminating the use of higher powers, we can protect the environment and retain a more sustainable habitat. Thank you for watching.